Alright, what up YouTubers? Welcome back to Structure Free Learning. And in this video we're going to do a simple calculation of the critical load for an I-shaped cross-section column that's 18 foot long, made of steel, modulus of elasticity 29,000 KSI. Here I've chosen a W16 by 77 to represent the column, and if you're familiar with the AISC manual, you'll be able to look the shape up and find all the geometric properties that I'm showing you here. Area, moments of inertia, and the radius or radii of gyration. The thing to note here is that the strong axis of the column is the horizontal axis through the geometric sense, where this XX represents the strong axis or the largest moment of inertia. This axis here represents the YY or the weak axis or the minimum moment of inertia. If I look at this column here and the way that I've drawn this, the support systems are set up so that I have a pin and fixed about the weak axis. Here, this would be weak axis buckling. In this column here, I would have strong axis buckling. So this drawing on the right represents buckling about the strong axis, and this diagram on the left represents buckling about the weak axis. Now what you'll see here is that the boundary conditions down here for the weak axis buckling, this is fixed about the y-axis and this is pinned, whereas here this is pinned about the strong axis or the x-axis, and it's also pinned down here. The way that the connection is built is such that you can transfer moments if you're bending about the y, whereas if you're bending about the x, there's no moment transferred. And the length is 18 feet. Now these boundary conditions will affect the buckled shape, and that will affect the effective length factor. Well, the thing that we want to do in this problem is calculate the elastic buckling load using the Euler critical load equation, which looks like this. And I've written the equation out in terms of the slenderness ratio KL over R. Now the first thing I normally like to do is calculate geometric properties, but it's all been done for us and it's tabulated and available out there. Now the next thing I want to do is determine the effective length factors, and that means having an understanding of the boundary conditions and the buckled shape. For strong axis buckling, or buckling about the x-axis on the right, my buckled shape here, because it's pinned and pinned, looks like this. Just sinusoidal shape here, and in fact the buckled length is the same length as the column, this 18 feet, and so in this case kx equals 1. And then here I have a pin and fixed shape, and so when this column buckles, or if it buckles about the y-axis, it would look like this. I would have zero slope because of my fixed condition here, and then I'd have a kind of a buckling out over here. This length right here is 70% of that buckled length, and so this ky would be 0.7 in theory. Now that I know my effective length factors, what I want to do is determine the governing slenderness ratio. So that slenderness ratio is this KL over R. And so I already know my radii of gyration, Rx and Ry. I have two slenderness ratios, one about the y-axis, one about the x-axis. What I want to do is choose the maximum of the two. And what it tells me is that whichever slenderness ratio is larger, that is going to be the axis about which this column will buckle. So if kx lx over rx is larger, then I know that my buckled shape will be in the x direction, or about the x-axis, and it'll have this shape right here, this kx equals 1, this diagram here. Whereas if the slenderness ratio about the y-axis governs, then I'm going to have this buckled shape over here on the left. And to compute the slenderness ratio is just a matter of plugging and chugging. So if I substitute the numbers here, the length, effective length factor for 1, the length 18 feet, the unit conversion, and then divided by the radius of gyration about the x, and then I do the same for the y-axis. Here I'm going to calculate that the slenderness ratio is the max of these two numbers. Notice it's the slenderness ratio, there's no units, so this is going to be 61.2, and that tells me that the weak axis governs. This large 61.2 tells me that the weak axis governs, and that means that my buckled shape, I anticipate, will look like here. This will be how my structure looks like if it buckles. And now all I gotta do is substitute it into the Euler buckling equation, and I'll be able to calculate that elastic buckling load. So here's the Euler buckling load with the values substituted in, and here this critical load, if I go through and calculate, it's going to be 1,727 kips. Now you got to note that this number here, this equation, assumes that my material stays elastic, column is not crooked, and all those assumptions are actually very severe. And what it does is it really, crookedness and inelastic material behavior actually reduces the buckling load here. So it actually buckles sooner than this elastic load predicts. So what this final number means is that in theory, my column could take 1,727 kips before buckling. But there's other things that go into this design here, like crookedness and inelastic behavior that you'd have to deal with if you're actually designing a real column. Alright, so hopefully this video was helpful, gave you an introductory idea about the Euler buckling formula, especially for a steel column, if you will. And let me know if you have any questions. See ya.